So in this session now, we will be looking at the design, how to derive the design equation for CSTR. Recall that this is called continuous stirred tank reactor. So when you want to derive a design equation, like I said, it's crucial to know that you have to start from the general mode balance equation, which is called GMBE. So GMBE, which is general mole balance equation, it is given by, again, let's take that in this chemical reaction, we have A converting it into B, right? Converting it into B. With my pen. Okay, comes back into B. So So now what's happening over here is when we start at GMBE, we have, remember, we express this in terms of molar flow rate. So we have F sub AO minus F sub A plus the integral VR RA multiplied by dV is equals to dNA divided by dt. So this is the general mole balance equation. So after looking at this, now we are no longer doing the batch, we are looking at the CSTR. So this type of a tank, what's happening within it is we're going to look at the assumptions, right? Because we have the chemical reaction that is taking place within this tank. So when we talk about the assumptions for CSTR, we're going to look at what? We're going to look, there is, okay, by the way, for CSTR, we have, it's a tank that is designed in a way that we have a stream that goes into it, and then we have the stream that is leaving the tank. So the stream that is leaving in the stream that is going into the tank, it is considered as inflow stream, and the one that leaves, it is considered to be as of outflow stream. So F sub AO, it is the inflow, and then F sub A, it is the outflow, hence why it's negative to show that it is leaving the system. And then here now, based on the assumption, the integral of VR RA dV will be equals to, again, RA multiplied by V, just like how we look at it for the batch reactor. Recall that the CSTR can be the same as batch reactor, operator, small scale, and whatnot. The theory behind that, like I said, we're not more on theory. I'll just throw the theory that's necessary for us to be able to design the equation for this reactor. So what's happening over here is the reason why we change this integral again to that, it's because of what we call the perfect mixing. I have already explained that under the batch reactor. So this is due to perfect mixing, right? No variation in terms of volume. When the chemical reaction is actually unfolding within the reactor. And then again, another assumption is dN sub A divided by dt will most definitely be equals to 0. So here it's a new thing. Here we are talking about the steady state. There's no change in whatsoever, concentration, temperature, whatever, pressure. There's no change in any of those parameters with time. So that's why we say we have a steady state. Steady state. Okay, in terms of our accumulation, it's 0 in this type of a tank. So now we're going to combine these assumptions with our GMBE. How are we going to do so? We have FAO subtract F sub A, then there for our generation, which is chemical reaction. We're going to have positive RA VR is now equals to 0. So in this case, instead of, because we don't have time, if you have a look at what we did under the batch reactor, we made our time the subject of the formula. That's what we are looking for, the time of the time that the batch reactor operates at. So here we don't have time, we're going to make volume the subject of the formula. So most of the times, if we want to determine the size of the reactor, we refer it to as its volume. So we're gonna make volume the subject of the formula. V of reactor is equals to, I'm gonna transpose this guys this side of the equation. So I'm gonna have negative FAO plus FA divide by RA. So to eliminate that, I'm going to take this negative out to put it on RA. So we have VR, we have FAO, subtract FA. I took my negative outside, but I'll take it to negative RA to show that this is the chemical reaction for the reactant. And so, I mean, the rate of reaction. So it's negative because we are referring to the reactants. So then we are done. This will be our design equation. But like I said, on batch, I said to you, this will be the design equation, depending on how you're supposed to derive your equation. But say maybe you are given the concentration, you are also given the what? You are given the concentration, you are also given the K. You can actually introduce concentration in this equation however you want. And again, it depends whether you are told that, if you are told, yes, the direction it is first order or second order or nonlinear, then that's how you can also introduce your rate laws by introducing concentration as well, just like how we did under the batch reactor. So for an example, let's say maybe we have what? We have, let's say it's first order. So our negative RA, we're introducing the rate law, will be equals to K multiplied by CA, right? So the moment we introduce the concentration, obvious, we're going to have to substitute it over there at the top. We also supposed to introduce our molar flow rate in terms of concentration. So stoichiometry, we know that to get the concentration, we can make use of the equation FA or FAO is equals to volume. How to get the concentration? Yeah, it's gonna be volume. And by the way, this is a specific volume because recall that F, it is the molar flow rate. So we need the volumetric flow rate as well, multiply by the concentration, is it? Yes. So remember, N is equals to, C is equals to N over V. So if you want to make the number of moles subject to the formula, we have to multiply C and V. Like I said, this is the molar moles in terms of rate, molar flow rate, and this will be the volumetric flow rate. So it's important that to denote that this, it's just a V with a cap on the top, which indicates flow rate, how we have learned from the fundamentals, right? So yeah, so this is how we can also introduce our concentration, right? And then again, here's the thing that I want you to understand, that most of the time, this is under the conversion factor. When we have the conversion factor, we know that we can also introduce this CAO, or we can say CA in fact, and I'll tell you, we can say CA is equals to CAO into 1 minus X. It's when we introduce the conversion factor, but I don't want to talk about this now. We will talk about it later on when we do the conversion factor, okay? So yeah, you will see, I will incorporate all of this so that you can understand how we can also rewrite this, because this is simple as algebraic, it's not the integral one. So this is just the algebraic, so it's simple, we can go through it and so forth. So I'll just end my design equation over here, okay? All right.